In our next section, we're going to look at some of the basics of IPv4 and IPv6 routing in JunOS. Specifically, we're going to talk about how IP addressing works. We'll see there's some minor differences between iOS's configuration of IP versus JunOS at the link level. We'll talk about how static routing works, what are some of the different options that we have at the end of the static routing statements, and then also how virtual routing and forwarding instances are implemented in JunOS. Now, as I had briefly mentioned before, one of the minor differences from a behavior point of view in JunOS versus iOS is that in iOS IP addressing, you normally have one primary address and then you can have multiple secondary addresses. In the case of JunOS, you can configure multiple interfaces at the link level, and by default, the lowest one is going to be the one that is the primary and what is also called the preferred address. So there's two separate attributes of the interface, both primary and preferred, where primary means that this is going to be the source for broadcast and multicast packets, or in other words, this is where the router would source its control plane packets. So if we wanted to establish an OSPF adjacency, then we're going to source the packet from the primary address, because OSPF normally is going to be using multicast for the hellos and for the basic protocol exchange. We also have the preferred address, where the preferred address is the one that is going to be used when we're talking to people that are on that local subnet, or in other words, for link local communication. Now, we can configure an address as both preferred and primary, and then those are configured under the address family INET at the individual link level. So, for example, if we were to take a look at our logical topology here, and let's say that we're talking about the link between the SRX and the 7200, which is going to be right here, this interface GIGI 000.46 on VSRX2, and then this is the subinterface F00.46 on the 7200 side. So right now I do have the IP addressing pre-configured both on the JunOS side and on the Cisco side. If we were to look at this from the iOS side and look at the show run interface F00.46, we have our subinterface that specifies what's the VLAN that's defined as the encapsulation, and then we have both the IPv4 and the IPv6 address. So right now there's only one address both for IPv4 and for IPv6 at the link level there. Now on the JunOS side, which is VSRX2 in this particular topology, if we look at the show config on interface GIG E000.46, which is unit 46 again. Okay, so .46, the naming convention here would be the same as saying show config interfaces GIG E00000, there's too many zeros, unit 46. So those configs are, or those pieces of syntax, those are identical there, where we're saying we have VLAN 46, so that's our encapsulation, and then we have our address family. So we're running both IPv4 and we're running IPv6. Now for IPv4, we have two different addresses configured. We have 10.1.46.4 and we have 10.1.46.3. Now for 10.1.46.4, we have two different attributes. We have it configured as primary and we have it configured as preferred. So if we were to go to the 7200 side, and let's look at the debug IP ICMP, and let's say that we were to do a ping from the JunOS side. We ping 10.1.46.6, which is the address here of the iOS side. And the packet is going to be sourced from 46.4, where 46.4 is the one that's configured as both the preferred and the primary address on the JunOS side. We can see it there is both preferred and primary. If we look at this from the set syntax, if we were to say show configuration interface GIG E000.46 pipe display set, and let's go to global config and let's delete the primary flag. And actually what we can do is, let's do it this way. Let's say edit interfaces, GIGI 000, unit 46, edit family INET address, and the address is 10.1.46.4/24. I'm going to delete the flags that are primary and that are preferred, and we'll commit it. Okay, next, if we were to send a ping again, let's run ping 10.1.46.6. Now the packets, notice, are coming from a different address. They're coming from 10.1.46.3 because that's the lowest address that's configured on the interface. So the point being is that you can have multiple addresses, but if you want to specify that when you do a peering with the router, like you do BGP peering or you do an IGP peering, and you want the router to be generating the packets from a specific address, then you need to specify that it is either primary or preferred or both, where again, primary is affecting broadcast and multicast. The preferred is affecting the link local communication. So for example, if we were to, let's say we turn IGP on, and we're going to come back to this and look at this in much more detail later, but let's say on the 7200 side, if we were just to say debug IP packet detail, and on the JunOS side, let's say let's go to top, and let's say edit protocols, OSPF. We're going to set area 0, interface, gig E000.46. Commit. Okay, that's turning the IGP process on. Then from the iOS side, and we're going to have to wait until the wait timer expires here for OSPF. If we top show OSPF run show OSPF interface gig E000.46 detail. What is the state of the link? State is waiting. Okay, so we're waiting 40 seconds for the dead timer to expire before we start to send hellos. Okay, once we exit the wait state, state is DR. And let's see this. On the 7200, I may need to turn IGP on in order to get this output. Let's say router, or let's do this. Let's go to the link level and say IP OSPF 1 area 0. So if we see, notice here, you can see it's kind of went by fast, but let me scroll back up a little bit. The hellos on the link level are coming from both of these addresses, 10.1.46.4 and 10.1.46.3. And if we then look at the show IP OSPF neighbors, basically we have two adjacencies, which doesn't necessarily make sense. So you can have multiple addresses, but normally you would want to set one as primary and preferred, because then you don't have multiple control plane protocols that are running redundant on the link. Now, if you only have one address, then that's fine. It's going to be sourcing the control plane from that particular address. But keep in mind that if you, like in the case of iOS, if we were to do this, if we go to the link level and say IP address 1234/24 and then show run on the link, do show run interface F0046, this is replacing the address. But in the case of JunOS, when you set the family INET, you're adding to the list, you're not replacing. So unless you use the replace command or unless you delete and then set, it's just adding it as additional addresses to the interface. So again, the way that we could fix that is either by just having one address, that would be the simplest way. But if we top show interface gigi 00046 family INET, we could edit that, top edit, and we will edit the address, edit address 10.1.46.4/24, set it to primary and set it to preferred. Then we'll commit and quit. And if we go back to the iOS side, let me repaste that address that was in there before, which was, actually, let me just configure it. IP address 10.1.46.6 then do debug IP packet detail. So it actually should be sending it only from one address. We'll come back to this when we talk about IGP, but just keep this in mind that it is a difference in the behavior that you can't have multiple primary address. Well, technically not primary addresses. You can't have multiple addresses when you configure them. Normally in iOS, it's going to override that unless you issue the secondary command. Now for IPv6, they're both going to behave the same. That you can have multiple addresses that can also be on different networks. They don't have to be in the same subnet. But when you are running the control plane, you then want to tell it what address is going to be primary, which address is going to be preferred. Now, in terms of routing, and we will, of course, like I mentioned, we're going to come back to IGP and BGP later. But in terms of static routing, this is going to be under configuration mode, and it's going to be under routing-options. So routing options would be things like static routes in this case, or if we were to say config, edit routing-options, and set question mark. So this is where we set static routing. Also other options like the router ID, where in the case of JunOS, the router ID is global to the system as a whole. It's not set under individual protocols. Like in the case of iOS, you can have an OSPF router ID, a BGP router ID, an LDP router ID. For JunOS, it's just one globally that's going to affect all of the control plane. Where in our case here, we're trying to configure static routing. So we're under edit routing options. We're going to edit static. And we're going to edit static routes. And then we want to say, what's the destination that we're trying to reach? Okay, so if we set, and we're under routing options, I should have said actually not set static route. Set static route, and what is the destination? So here we're on VSRX2. If we take a look at our topology, let's say that we're trying to reach the loopback of the 7200. Okay, the loopback of the 7200 is 6666/32. So we'll say that's the particular prefix. And then what is the next hop? Okay, next hop is going to be 10.1.46.46.6, so that's the address on the other side. And we'll commit and quit. Okay, also we will turn OSPF off because we're not going to be doing dynamic routing right now. No router OSPF1. Okay, if we now do a ping at 10.1.46, actually no, ping 6666. Okay, we can see we do have connectivity to it. Now, in terms of the routing tables for JunOS, we'll see that there's going to be multiple tables depending on what particular protocols that we are dealing with. But in the case of iOS, normally you would say show IP route, show IPv6 route, show MPLS forwarding table, show BGP. Show the BGP table. In the case of JunOS, mainly we just say show route. And show route is going to essentially be all address families, and it's also going to be all VRFs and subtables. Where in this case, we see that there's a table that this is called inet.0. inet.0 is basically the global IP routing table. So this is the equivalent of what you would have in show IP route in iOS. Then after this, we should have the IPv6 table, which is going to be inet6.0. And we should see that we have not only unicast, but also multicast listed in here, where 224.0.0.5, this is for OSPF version 2. And then we have our static route that is 6666/32, and then we have it pointing towards our particular next hop value. Now, in terms of IPv6 static routing, and this is also under routing options, but it's going to be under the RIB, the routing information base, INET 6.0, where when we set routing options static route, that's talking about INET.0, which is the regular global unicast to IPv4 routing table. So if we want to do static routing for v6, it's similar in syntax, but we need to make sure to add this keyword here, which is RIB INET 6.0. So if we wanted to do the same thing, let's say for the IPv6 address of the other side, we would go to Edit Routing dash Options. We're config first, config, Edit Routing dash Options. We're going to set a route or set a static route. And the static route is, or actually we need to say static, set static, no. The RIB comes first. So we say set RIB. What table is it in? The table's name is INET 6.0. So that we have a static route, and then what's the destination? So if we say that it's their IPv6 loopback, which in this case is 2001:6666/128. And then how do we get there? And the next hop is going to be their global unicast address, which is, if we go to the other side, and we show run interface F0046. Okay, that's the next hop. If we commit and quit, and then show route, we could just say show route, which again is going to show all the tables. But if we say show route and then specifically the table, this would be filtering it based on the address family. So if we say show route, the table is INET 6.0, then that's the equivalent of show IPv6 route. Or likewise, if you show table INET.0, that's the equivalent of show IP route in iOS. But the logic is going to be the same, that you can have multiple different protocols. We have static, we have dynamic. In terms of dynamic, we have OSPF, RIP version 2, IS to IS, BGP. Same parallels in IPv6. We have RIP-NG, we have OSPF v3, ISIS, and BGP. And we'll see once we go through the configurations, we'll talk a little bit more about the format of the table and what happens if you have multiple dynamic routes and like you're competing with one match over another. But in this case, we can see that we have the static route installed. It's to the directly connected neighbor, and we can see that the router already knows that this is going to recurse to gigi000.46. So if we were to do a ping to 2001::6666, we should be able to get reachability because we're directly connected to that neighbor. Now, there's some other key differences here, though, between the JunOS behavior and iOS. One of them is that the static routes are not recursive by default. So this means that if you configure one static route that points to another route, it's not going to be able to find the outgoing interface and actually install the route by default unless we add the resolve keyword. So for example, we have a situation here where there's one static route. In this case, it's a static default route. So it's an INET 6 route, so it's IPv6 route for ::/0, which is our default. And it says the default route points to the next hop 2001::1. Now, assuming that 2001::1 is not on a directly connected interface, there might be some other intermediary route that's pointing towards it. The router is not going to be able to install this in INET 6.0 into the actual RIB and then into the fib. So by saying that we have the option resolve on the route, if we have another route that's pointing towards the next hop and we are somehow able to recurse it towards an interface, then we would be able to install it. So like in this case, if we were to say config edit routing dash options, set static route 1234 is via the next hop 5678. And if we set static route 5678 via the next hop 10.1.46.6, and then we will commit. And we run show route table inet.0, so that's the equivalent of show IP route. And I put in two different routes. I put one that goes to 1234, and I put one that goes to 5678. Now, 5678 was installed because it was able to recurse towards the directly connected interface. Or in other words, when the packet comes in, the router knows what link to switch it out before it does the encapsulation. But with the previous route, 1234, that's not resolved or recursed to a physical interface, so it's not able to do the installation. Where in the case of iOS, routes are recursive by default, that you can have multiple levels of one route pointing towards another. But in this case, if you did want to do that, we can do it for the route. We just have to say that that is an option on it. Where we would edit static, we would edit the route 1234/32, and then set the resolve option onto it. Commit and quit. Then we will show config routing-options. And we can see that there's two different ways to denote the route. If there's no other attributes besides just a prefix and then the next hop, it shows it all in one line. But you can do an edit where you're editing the prefix and length and then setting different options under there. And if we show config routing options, pipe display set, we can see what are those set commands that have this result. But now if we look at the show route table inet.0, now both of the routes are installed. 1234 points to 5678, and 5678 points to 10.1.46.6. So via the recursive property or via the resolve function of the route, it means that 1234 is via 10.1.46.4. Where, like I mentioned, in the case of iOS, this would be the default option where routes are recursive. Okay, another option is the reject keyword. Reject keyword is when you want to do null routing, so you want to discard a packet, but you also want to respond with an ICMP unreachable. So, for example, if we were to say on this particular router, let's do let's say we go to the 7200 and we're going to do a default route that points at SRX2. So in global config of iOS, we're going to say IP route all zeros. Next hop is 10.1.46.4. Okay, that's VSRX2's address. Now on the SRX box, we're going to say config. We're going to edit routing options. We're going to set a static route. Set static route. And let's say the address is 10.10.10.10/32. And the option is going to be reject. Commit. Okay, now on the 7200, when we go to send traffic to this, if we were to ping 10.10.10.10, it's going to follow our default route, and then we can see we get ICMP unreachable back in. If we were to debug IP ICMP, we can actually see the return code, which should be network unreachable that's coming in from the SRX. So in other words, it says I don't have a route to that destination. Or in this case, technically, it does have a route, but it's a route that effectively goes to null zero, and it says to respond back with an ICMP unreachable. Now, if we were to say instead of reject, if we were to say discard, discard means that you are still going to drop the traffic, so you're null routing it, but you are going to silently discard it. And this is a different behavior than iOS, where in iOS you would globally say no IP unreachables, or at the null zero interface say no IP unreachables, and that would turn it off globally for the system. But in the case of JunOS, you can say on a per route basis, do you want to just silently discard the traffic, or do you want to discard it and then reply back with unreachable? So if we were to set another static route similarly, let's say set static route 11.11.11.11/32, but we are going to discard as opposed to reject. when we do a ping now to 11.11.11.11, the packet gets dropped, but the packet gets silently dropped, so we don't have an ICMP unreachable coming back in.